Of this conference, our first speaker is Professor Sorin bangu of the University of Bergen. He will speak about the question, the applicability of mathematics to the external world, which is very old. It was put on the philosophical agenda by Pythagoreans and Plato, and was revived in 1960 by Wigner in his paper, The Unreasonable Effectiveness of Mathematics in the world, natural sciences. This explains the fact.
Yes. Okay, thanks, Carlo, and thanks everyone for coming, and thanks to Emiliano and Fabio for organizing it. All right, so as Carlo already mentioned, the paper and the talk is going to deal with some issues raised by Wigner's paper, The Unreasonable Effectiveness of Mathematics and Natural Sciences. It's a famous paper, although I found about it only 10 years ago. It's the issue is not. I mean, although it deals with and touches upon things which are really, venerable in the philosophy in general, starting with Pythagoras and Plato. The topic is not really that popular in philosophy of mathematics. So, if you look, for instance, at Ontology by Axelrod and Putnam in 1980 was, I think, the first edition. There's nothing about the applicability of mathematics. The problem doesn't really exist. So, in a sense, it's an orphan topic in philosophy of mathematics. It was more of interest for physicists. So, when I first learned about the issue, I just looked through who said what about this, and the number of physicists, I think, was larger than the number of philosophers who had something to say about this. Somewhat surprising. And now, a couple of months ago, when I decided to speak about this, I checked again, and I know philosophers are catching up, but still, it's not extremely popular. So, although there are a number of important things that have been said about the issue. Now, so as I said, it's more of a question for physicists. And I was trying to find sort of a snappy sort of presentation of what a puzzle is in Wigner's paper. It's rather hard, so this is the best I could come up with. Somewhat interestingly, Paul Dirac, no less than 21 years before, managed to find to present the puzzle, the essence of the puzzle, in a sort of a much snappier way than Wigner. So Dirac talked about this situation, right, which is a situation taken in a history of science and in philosophy even. When we describe the situation by saying that a mathematician plays a game in which he himself invents the rules, while the physicist plays a game in which the rules are provided by nature. But as time goes on, it becomes increasingly evident that the rules which the mathematician finds interesting are the same as those which nature has chosen. Right, so that's Paul Dirac, 1939. It's probably not surprising that Wigner was familiar with this kind of situation, put it this way. They were, by the way, related. So Wigner's sister became Dirac's wife later in life. So I imagine that they're talking about this a lot. Anyway, so that's one way to describe the problem we're gonna deal with. The puzzle, as I said, became sort of an important question for important physicists, and here's Stefan Weinberg, who also presented it in 1986. It's positively spooky how the physicist finds the mathematician has been there before him or her. Now, what Weinberg and Dirac and Wigner have in mind is this kind of sort of historical / scientific / philosophical succession of developments in mathematics and physics, right? So we have a physical theory which is preceded, sometimes even by a couple of hundreds of years, by some mathematical development. It just happens that whatever mathematical theory or mathematical apparatus they needed in in physics was developed previously by mathematicians. I guess everyone is familiar with those correspondences here and complex numbers discovered or invented 1600, central in quantum mechanics. Non-Euclidean geometry was essential for developing general relativity. This area of mathematics here, the theory of continuous groups and group representations, was developed by Sophus Lee and Lee Cartan at the beginning of end of 19th century, and then was used later on heavily in the 20th century in describing and classifying elementary particles. So yeah, here is yet another statement of the problem, of the situation, right? So it's not only that the mathematician has been there before, but the reason the mathematician has been there is just pure aesthetical interest. Right? So here's Weinberg again. Mathematicians are led by their sense of mathematical beauty to develop formal structures that physicists only later find useful, even where the mathematician had no such goal in mind. Physicists generally find the ability of mathematicians to anticipate the mathematics needed in the theories of physics quite uncanny. It is as if Neil Armstrong in 1969, when he first set foot on the surface of the moon, had found in the lunar dust that was the fuel there. All right, so this should give you a feel of what the problem is, right? What the general issue at stake is. In terms of what I'm gonna say today is. I will begin with some clarification of trying to give you a bit more clear version of presentation of the puzzle, because the puzzle comes in several versions. So that's one of the things that typically puzzles people these days. So yeah, so it will be this. This section of clarification and also presentation. I'll also touch on some recent take on the puzzle, which to my mind is just a misunderstanding of what's going on in this case by Alvin Plantinga. Right? So he wrote a book in 2011 in which one of the chapters is devoted to the puzzle, and the attempt is to Plantinga's attempts to use the puzzle somehow to support his rational theism. Right? Okay, so then I'll go over a number of solutions that were proposed to this puzzle. I know 5 solutions, and we'll try to be as clear as possible what they are. But if you happen to know some more, I'd be just eager to learn about it. Now, 4 of those solutions seem somewhat okay to me, but there are, as you'll see, there are serious issues with them. I should say that they look okay and they seem convincing, but if you dig a little bit deeper, you'll see that things are not entirely fine. Now, my favorite solution, I just call it over-determination solution. You'll see why. I don't like this term particularly, well, but it's just, I couldn't find any other. Now, in the end, so I'll finish the talk with the problem for this best solution. I take it to be. I think that even that best solution is still open for debate. Okay, so in the end, I think the message is that, well, the puzzle is still worth discussing and reflecting on. Okay, so by way of clarification, beginner speaks about the effectiveness of mathematics. Now, what is effective? Well, the language of mathematics. What he means by that is modern mathematics. Right? He never, circumscribes. It's a bit vague about what modern means. But in terms of his examples, the examples of mathematical concepts and structures he uses in his paper are not the elementary, circles, squares, and curves maybe. So he presents the issue, he raises the issue in terms of modern mathematical concepts. What is this language effective for? Well, it's effective for or in the formulation of the laws of physics. So he is particularly interested in the effectiveness of mathematics and use of mathematics in the description of natural phenomena. Right. Now, I'm saying this, although those two things are relatively clear from his paper. There are other things which are much more faulty, but I'm saying this just because there is another version of the puzzle by Mark Steiner. It's a heuristic version of the puzzle. And according to Steiner, who takes his cue, as it were, from Wigner, Steiner presents manufactures a puzzle in terms of the effectiveness of mathematics as a tool of discovery of new laws of nature. Right. So what Steiner says in a nutshell is that, well, mathematical analogy served as a way of as an engine for theory discovery or theory invention in the history of science. So start from classical mechanics, by mathematical analogy you arrive at some quantum laws, and then even within the quantum domain you use mathematical analogies to invent or to propose other mathematical mathematically formulated quantum laws. Right? So this is a puzzle which is I wouldn't say orthogonal. Right? And it's not orthogonal. It's not parallel. It's somewhat intersecting, crisscrossing the Wigner puzzle. There are interesting differences and similarities, but I will not get into this at all. Right? In my view, this is Steiner's. Well, obviously, with the benefit of insight, Steiner's puzzle is much harder to solve. So, but for us today, we'll just deal with the Wigner puzzle. Okay. So as I said, there are two versions, or two ways to, if you read the paper, there are two ways to understand what Wigner wants to say there. So there is a version somewhat superficial. It's how Wigner seems to argue. If you look at the paper, and then I'll also present a chart of a reconstruction of his position. In particular, because the kind of superficial position, or the superficial argument he makes, it's patently invalid, right? So what he seems to say is that, well, here are a bunch of concepts, and then they are unreasonably effective, and then those concepts are mathematical, therefore mathematical concepts, or mathematics in general, is unreasonably effective, right? So obviously what follows is just some mathematical concepts are unreasonably effective. What remains to be seen is what this unreasonable effectiveness has to do with those concepts being mathematical. That's not entirely clear, or at least you need to do a bit of reconstruction of the paper to see how this works. Even if this is even if we go with this conclusion, or weaker conclusion, I think the idea is that we can deal with the puzzle on a case-by-case basis, and in the end, the mystery kind of evaporates, right? So, my impression is that this version, which many people have in mind when they comment on the puzzle, it's not really worth discussing. Now, this is the chart of a reconstruction. It's not entirely mine. I mean, there are a couple of authors who worked on this, some detail. Mark Steiner, Penelope Maddy. I've even seen that Stephen French had some interest in it. Maybe, other people. So I kind of put together this version of the puzzle. So 3 premises and one conclusion. Modern mathematical concepts reflect our, or mathematicians' aesthetic preferences, as we've already saw hinted by Dirac and Weinberg. Second premise, what originates in this aesthetic sense should not be effective in physics, and thus it is unreasonable if such concepts are effective. Third premise, yet significantly many mathematical concepts are effective in physics, therefore it's unreasonable that mathematics is so effective in physics. Right? Now, what I mean all the way is that talking about modern mathematical concepts, and we're talking about a significant number of them, right? So, so that's the version of the puzzle I'm going to deal with. Now, what I'll do is just go over each premise quickly. I hope I'm right. It's valid. It's a valid argument. So now, obviously, we'll have to check for soundness. So what about the first premise? Well, the first premise is strikes me as a factual claim, right? So it's the idea that modern mathematical concepts, advanced mathematical concepts, stem from this aesthetic sense or reflect this aesthetic preference. It's a claim that in the end can be sort of checked by looking carefully at the history of mathematics, as the sociology of mathematics, for instance. Can you think of counterexamples? What about calculus? Well, yes. So calculus was invented precisely in order to deal with the physical problem. But put this aside, right? There is enough material. There are enough cases where I think this premise can be supported. Right? So that's a claim, after all, about the nature of modern mathematics. And Wigner presents this his view of what mathematics is in a couple of places. So those are just sort of collected those quotes from various places in the paper. At the beginning of the paper, he says that mathematics is the science of skillful operations with concepts and rules invented just for this purpose. Mathematicians demonstrate their ingenuity and sense of formal beauty. The principal emphasis is on the invention of concepts. Right. So pretty clear that this is, one way to capture what he wants to say is this way. There are other people, and many other people, I should emphasize that many people agree with Wigner, and I imagine that disagreement was reached independently. So Richard Hamming, the famous computer scientist, says similar things. Artistic taste plays a large role in modern mathematics. We have tried to make mathematics a consistent, beautiful thing, and by doing so, we have had an amazing number of successful applications to the physical world. Right? So that's yet another statement of the puzzle. Good. So, just to prepare the terrain for discussion later on, what I want to draw your attention to is this sort of anti-realist setting of in which the problem is presented. Right? So Wigner talks about the invention of concepts. Right? Hamming talks about the way how we make mathematics. Right? So this anti-realist assumption, in a sense, it's present, or it's fundamental for the puzzle. There's a separate question whether you can raise or you can sort of reconstruct the puzzle within a realist set. I'm not sure if that's possible, but that's a separate problem, right? So if you have this in mind, then we can discuss it in Mark Olivan has a paper on this. I'm not sure I agree with everything he says, but that's a sort of a relevant question, because everything that Wigner says is sort of has this anti-realist flavor. All right, so let's move on to the second premise. What originates in our aesthetic sense should not be effective in physics. Unless it is unreasonable if such concepts are so. What this premise brings is yet another anti-realist sort of tone. This idea that the criticism that anti-realists raised against this thought that our so-called pragmatic virtues, right, non-epistemic virtues, should conduce, right? So an anti-realist would object to the inference of the best explanations, for instance, because there is no reason to believe that whatever seems best to us should be actually true in nature, right? So the contrast here is roughly speaking, between this subjective and objective side of things. And there's even more endorsement from other giants of theoretical physics, Freeman Dyson. Why should nature care about our feelings of beauty? Why should the electron prefer a beautiful equation to an ugly one? Right. So that's the second premise. Now the third premise says that significantly many mathematical concepts are effective in physics. Now, this strikes me as yet another factual claim. And after all, it's just it comes down to how we count, right? So it's just it's a question about how many concepts are applied. So that's one way to understand this question. Or maybe it's a question about, in addition to that, it's a question about how many times one and the same concept is applied. Right? And also, it's very important here to be able to evaluate the ratio of successful applications to failed applications, right? After all. Right? So if we were to get into the nitty-gritty details of those claims, then we end up with analysis like this. Okay, so this is the final the version of the puzzle I'm going to discuss from now on. And just to get back to Plantinga, the point I want to make is that he simply seems to misunderstand what the puzzle is about. The way he presents, the idea he's appealing to is that, well, mathematics is, after all, in a sense, product of the mind of God, right? So it's not really Platonism. It's not really Platonist realist. It's probably some version having to do with Christian theism or something like that. So, but the general setting in which he discusses the puzzle is this strongly realist position, right? While Wigner, as I hope I convinced you, it's just taking an anti-realist line. So it seems to me that although I appreciate Plantinga bringing in discussion the puzzle and the issue, I think he simply misunderstands what's going on here. So there's no way. I mean, there may be other ways to support theism, but Wigner puzzle is not going to do him any good. All right. So what I will do now, or good in time. Yeah. I'll go over the solutions, right? The 5 solutions I mentioned at the beginning. As I said, they are not mine. Yeah. Well, I wrote about this stuff before, but not claiming any originality here. Maybe just in arranging things and clarifying some relations. But you can find them in the literature, right? So if you look through the papers, it's all there. So there are 5 solutions. I used to like number 3 a lot in the past. Now I switched to number 5. So the first 4 solutions I think are relatively easy to sort of fault or to raise issues with. Number 5 seems to me the most stable and the best solution so far, yet not good enough for someone who is sort of a stubborn Wigner defender. Okay, so why it's not unreasonable that mathematics applies effectively? Well, because in fact the whole thing is just an exaggeration. There are many failures in applying mathematics, so the whole issue is in a sense just doesn't exist, right? So there's no problem here. The second solution says that, well, yeah, but if you look at the mathematical concepts, they have empirical origins, therefore, you have this common origin type of argument. It's no surprise that they apply. The third solution says that mathematics involves modeling, right? So we prepare, after all, when you apply a mathematical formalism to a physical system, we prepare that system in order to apply mathematics. So there is no surprise after all. And this has come up a couple of times in the discussion here. Then there is the fourth solution, saying that our mathematical aesthetic sense is shaped by evolution, therefore sensitive to environment. Therefore, you can see the connection here. Whatever originates in this aesthetic sense, there's a good chance to be applied after all back to the environment. So that's the fourth solution. Now, the fifth solution is maybe kind of a simplest one in a sense. It's a brute force solution. Well, it says that there is a lot of mathematics to choose from, right? And therefore, at some point, it's just going to happen that some of those formalisms are going to needed in physics after all, right? So it seems to me that the fifth solution is the least problematic one, right? Although you'll see, I'll raise an issue with that in a moment. So quickly, what is the first solution? Well, there are many failures in applying mathematics, and this attacks the third premise. I would say yes. So again, just in a sense, playing devil's advocate for a little. I would say yes. Yeah, sure. There are many failures, and the premise is rejectable, but it doesn't strike me as obviously false, right? So if we are in the end, if we're told how to count, if we're told what the ratio is, it's conceivable that this counting might or may vindicate the figure. So yeah, that's a way out to appeal to this maybe the ratio, let's say the ratio argument. But in the end, I don't think that someone like Wigner would be extremely convinced by it. We can move on to the second solution, which says that mathematical concepts and structures have empirical origins. And here we have Ernst Nagel putting it in a very simple and nice form. It is no mystery, therefore, that pure mathematics can so often be applied because the symbolic structures it studies are all suggested by natural structures discovered in the flux of things. It's a very appealing solution. And I agree that it's devastating if it would be true, right? In fact, it's problematic, I think. And other people pointed out to this issue. Well, yes, basic concepts, right? Basic geometrical concepts or basic arithmetical concepts have empirical origins. There is no question about this, and Wigner is eager to grant it at the beginning of the paper. Yet, if we look at modern concepts, right, the important modern concepts, they typically don't have empirical origins. So they are a reflection of one mathematician's like, what they think is interesting, how they, what allows them to show their ingenuity in developing their theories, right? So I think this is an issue for the empirical origins solution. All right, the third solution, as I said, I liked it a lot in the past. Now I have some sort of doubts about it. Applicability involves modeling, and then because the application of mathematics is always sort of a two-step process. You first look at the system and then sort of select what you want to understand about it, you model it. Therefore, it's no surprise that mathematics gets applied in the end, and a large amount. So this is Frank Wilczek putting it in this archery metaphor. One way to succeed to archery is to draw a bullseye around the place your arrow lands. Right? I'm going to use this metaphor in a moment again. Still from Wilczek. Another sort of another way to put the same idea, roughly the same idea, was proposed by J.T. Schwartz. Mathematics is able to deal successfully only with the simplest of situations, more precisely with a complex situation, only to the extent that rare good fortune makes this complex situation hinge upon a few dominant simple factors. Right? So, if you want a slogan, model it until you can apply it. So, if this is the strategy that works, then obviously mathematics is applied to a large extent. Now, I wonder if that's true. I mean, obviously it has a ring of truth, right? So this happens a lot in physics. Now the question is, how rare is this good fortune? I'm not so sure. I think it happens way too often to dismiss it easily. Now there is a variation on this theme. It's called a selection effect by Wilczek. He says things like this: part of the explanation for the success of mathematics and natural science is that we select what we regard as scientifically interesting aspects of nature, largely for their ability to allow mathematical treatment. Right? So bother with it only if you can apply it. That's the message. And again, I think he goes on by giving some examples which I wasn't able to understand from, I don't know, ultra cold physics, whatever. But the main idea is that you want to make theoretical progress, and then sort of look for, you know, when all you have is a nail, or how is that? When all you have is a hammer, everything looks like a nail, something like that. So again, there is again something to it. I'm not denying it, but I would say that this is just only part of the explanation, and it seems to me too extreme. It seems to me that there are processes and natural phenomena which somehow impose upon us as scientifically interesting, regardless of what mathematical formalism we have available, right? So again, it strikes me as too extreme. All right, our mathematical aesthetic sense is shaped by evolution and sensitive to environment. Therefore, the second premise is problematic. Well, yes. I mean, I can see where this is coming from, and I'm even willing to agree that our aesthetic sense in general does reflect our adaptation to physical environment, in mating behavior, for instance. So I think that there is definitely something to it. So our aesthetic sense is not just entirely, completely coming out of nowhere. But what we're talking here about is mathematical aesthetic sense, and I'm not so sure that. So we're talking about highly formal sort of domain of intellectual domains. I'm not so sure that evolutionary pressure can have such an important role here, right? So it seems to me that mathematical aesthetic sense is much less sensitive to pressures from environment than evolutionary type of argument, right? So again, yes, rings true, but again, I think there are issues. Now, the fifth solution says that, as I already mentioned, well, there is a lot of stuff to choose from, a lot of stuff to apply, and then. Well, at some point, a lucky accident is bound to happen. It's just again this fact about nature, about mathematics, about profession, about the field of inquiry. That there is a lot of stuff available to try out, and at some point, once in a while, that's going to happen. Right? Applicability is going to happen. So again, in terms of the archery metaphor, imagine having many arrows, thrown at shot at the target. Even if it's a small target, right? Some of those arrows are going to hit the target after all. So no mystery that sometimes you hit. As a physicist, you find somewhere in the large area of mathematics some concepts, some notions, some theories which will help you. Now, all fine. I think it's just perfectly okay. And this, in particular, deals with this issue of origins, which I wasn't happy about earlier on. And this type of solution, I think it allows the claim that the origin of the arrows is irrelevant. But there is this problem, right? And I'll formulate it in terms of gesturing a bit rather than formulating it carefully in terms of examples. There is this problem that the target will get hit only if the arrows are shot in the right direction, in the direction of the target. If they are shot in a completely different direction, doesn't matter how many you shot, the target is not going to be hit, right? So I think in order to appeal to this solution, you need to make another factual assumption. Namely that there is not only a large amount of mathematics available, but a large amount of mathematics of the right kind, right? Which means we need to have a large amount of diverse kind of mathematics to choose from. And I think this factual claim, which would solve if true, would solve the problem. I think it's rather hard to defend. Again, it all comes down in a sense to assessing how those facts are in terms of how much mathematics is available. Right. Okay, so I'll stop here. I hope we have time for
questions. Yes.
A pretty dialectical question about the dialectic. Why not think that there's something to more or less every one of these 5 solutions? Why pick one?
Okay, yeah.
Why not think that they are all getting, explaining the part
Yeah,
of it?
yeah. Well, I chose this in my book, so I have a chapter on this, and I said, well, I mean, the title is something like the puzzling crossfire. So I said, well, we have so many solutions. I think the end is going, one of them is going to hit the. So yeah, I think that if you put all of them together and think about, well, we have a problem, so many solutions, then we're probably done with the problem. Right? So we're not happy with any in particular, but forming some sort of a sum of the vectorial sum of the solution, then it's going to. So yeah, I think you can say that. I think you can say that, and I'm relatively happy with it. But there is a paper by Alan Haig called 16 Arguments Against Classical Frequentism. Do you know about it? So he lists 16 arguments against classical frequentism, and at the end says, well, but then why do we need 16 solutions? That's 16 criticism. It means that the view holds certain appeal to us. Well, anyway, but yeah, I agree. Yeah.
At least I think one of the factors of why there's this correspondence is symmetry. That is, mathematical systems have symmetries, and physical systems have symmetries. And the symmetries of physical systems have very, very important causal consequences, or exhibit important causal features. And that's not a big surprise. I mean,
no.
What I said yesterday was that symmetry in space and time is often a sign of stability. So it's not surprising that physically existing things and systems exhibit symmetries.
Yeah, no, I think that's absolutely fine. And then again, I'm not going to defend say that doesn't solve the problem. So which one of those solutions do you think might fit the
kind of solution?
It's a new kind of solution.
Well,
okay.
It just comes in from a different direction.
Yeah, well, I would say, I would say it's probably.
You could hook it up to that if you want, but I don't think you need to.
Yeah. Well, that one type of answer I've seen when people point out to this is that, but there are symmetries and symmetries, and as it happens, mathematicians pick the right ones. Right? This is just they find the ones they find interesting exactly the ones which nature seems to have chosen, and they find those symmetries interesting regardless of any sort of considerations, physical considerations. So that's a possible reply, right? So we have, because the problem here is that if we are to accept the assumptions.
Well, there's finitary symmetries, and there's, I guess,
yeah. Well, so that there are many symmetries, and as it happens, mathematicians, just by pure reflection, somehow hit exactly the ones which.
That's the one other thing I would say, which is that, especially when you look at modern mathematics, let's say 19th, early 20th century mathematics, I don't see it driven by aesthetic considerations. I see it driven by a desire to solve problems.
But the problems themselves are considered intriguing and interesting and beautiful. So I should have probably insisted that this aesthetic consideration, the aesthetic considerations should be understood. Well, people talk about beauty, but beauty is an umbrella term, right? So what mathematicians look for is to simplify their theories, to find unity, to find elegance, to find so. They don't only want to find just solutions, they want to find good and interesting and
Sometimes they look for elegant solutions, but sometimes they look for messy solutions.
Yeah.
Sometimes it's a solution.
yeah, that's true. But they won't be happy for long with a messy solution. Try to, in a sense, bring everything into a anyway.
So, anyone S1 to S5 may be part of so I agree definitely that why pick one? I mean,
Yeah.
there are several arguments that they
Yeah.
S1 is not particularly interesting, so I skip it because it's S1 was there are many failures.
Yeah.
It is irrelevant to me. So okay, it may be there, it's really irrelevant. S2 we may speak for a very long time. It's just correct in the sense that one should look to the history of mathematics and even to the prehistory of mathematics, and there's much to learn. I would just like to make an example of S3 because that's interesting to me. So, do you think, or does anybody think, that what's going on in this very room now, which is a tiny portion of the universe, may be described by a simple equation? Simple, elegant, in the sense of the rocks.
I definitely think it cannot. Yeah.
So do I.
Yeah.
So, now I imagine I am Galileo Galilei. I am sitting in a room where everything is going on in such an irregular and complicated way. I cannot even imagine if the idea that there is an underlying equation is correct or not. Perhaps not. Then I see a lamp swinging back and forth, something regular. That hits my attention. Because it's regular.
Yeah.
It's like the motion of planets. And whenever it's regular, it's simple, there must be a rule, a solution to that regularity, to that simplicity. So we stick to simple things.
Yeah.
It's exactly the electron isolated, which is described by Dirac's equation, does not exist.
No.
In nature, electrons do interact.
They even
And
self-interact.
interacting electron is such a mess, we cannot describe them. We write equations, but we are not able to solve them. So we have a very vague idea of what happens when electrons interact. But there's nothing like a single electron in the universe out there. It's just a very, very simplified model. Single electron alone in the universe. Then it works, Dirac equation. Very nice, very simple equation. But so what? Electron interacts, there's mess, there's complication. So S3 is,
Yeah, no. This is why I like this tree for quite a long time.
Yes.
One question. The question is, since you focus so much on kind of the grammar perspective, that mathematicians always have been there already.
Yeah.
There seems to be a kind of a comparable, interesting phenomenon in mathematics itself.
Yeah.
So we heard Emiliano talk about how various mathematical fields enter one specific field, not here. There are other examples.
Yeah.
Recently, it turns out that statistical methods are important for several other mathematical fields and so on. So one might identify a similar problem within mathematics. My question would be whether you consider that a closely related problem or something. Yeah,
there are people who said exactly the same thing, that you have mathematics applied to itself, whatever, right? So, yeah, so could be a similar. I mean, I didn't want to get into that issue, but yeah, it is something that has been noticed, that you have. I mean, other mathematicians have been there before other mathematicians. It's a revolving door.
the history and the prehistory.
Yeah.
Yes, and the second point is that there is, in particular with respect to the fifth solution,
Yeah.
the origination explanation, there is sometimes, let's say, floating around, I cannot pinpoint the source of that idea, but there is this idea that the phenomenon is stronger than just there is some mathematics that does the job. There is also this impression that most of mathematics that has been developed at some stage enters physics. So it's very difficult to find a piece of mathematics that stays completely detached from physical use. So I think if one considers that a reasonable observation, then the overdetermination arguments would not apply, because it's more than just there is a lot of mathematics to choose from, but it's rather most of math actually.
Oh, okay, I see what you mean. But that's I mean, I guess you're well, yeah. If I understand you correctly, but I think this you take on you a sort of a serious burden to show that for at every point in time there is all mathematics is applied, and I don't think anybody would believe that. I think there's
well, not in the.
I mean, factually speaking, there are
way,
large portions of mathematics.
That will never say those tendency.
Yeah.
We don't know.
Yeah.
Yeah.
But I mean, I think his argument is that well, probably at every moment there is all mathematics is in a sense applied, or is that? I mean,
No.
are you committed to that, or
no? The argument would rather be that let's say the argument would rather be if we wait long enough, some piece of mathematics is developed, and we wait long enough, we can be fairly sure that some stage identity. That would be the idea. I don't know what
Yeah.
that's just.
I was wondering at some point, well, somewhat related to this, I was wondering at some point, because, you know, all mathematics is related, I mean, there are interrelations, so someone might want to talk about kind of indirect applications. I have a piece of mathematics which is applied, has a role in physics, and then this evolved from some other piece which is not applied, and then you can say, through some sort of transitivity of application, you can say that, well, maybe that second piece is applied as well. It strikes me as a sleight of hand, but I think it's reasonable to think about it, right? So in this sense, yes, all mathematics is applied.
Yes.
I like all these solutions, very eclectic too. And
Going to
even
sell
if
them.
the one that I like, especially like, is the Pythagorean Platonic solution that all the reality is made of mathematical objects. So we are made of mathematical objects, we are able to build things that are in tune with the reality.
Yes.
Okay, I have further questions. There is also an instrumental solution. For instance, human beings didn't use mathematics in the past, our ancestors, and they were able to manage nature with magic, with myths, with also instrumentally. Mathematics, not only there is another problem, mathematics is very rare in human beings.
Yeah.
Usually human beings do not like mathematics, are not inclined to mathematics.
Yeah.
Notwithstanding this fact, there is a success of mathematics, also because I think, this is not an epistemological explanation, this is not even a kind of philosophical explanation, it is a more and moral explanation, that through mathematics, human beings discovered that they were able to manipulate the world. This is linked to the solution 4 that we modeled. And we were able to predict in a good way, much better than with magic, religion, myths, nature, and so, this is typical of modern human being, to possess our own destinies. So this explains also the success of science, notwithstanding the fact that science is the product of a very infinitesimal part of human beings. Because I wanted to remember that mathematics is the product, science, but also philosophy, the product of very few human beings. Human beings are usually not inclined even to use in a good way the natural language. Not only yes, but this is true. It is provocative, but it is true. And for instance, Aristotle used narratives to make physics, but also narratives were in some sense good, but of course less predictive than Newtonian mechanics or other scientific theories that were able to make the human able to make artifacts.
Yeah.
that affect also the human beings that do not like mathematics and science. So more questions.
Okay. Yeah. I mean, just a quick point is that the puzzle is raised by those modern mathematical concepts, not so much by the ones we use in direct manipulation of nature. So yeah, when it comes to those concepts, I mean, I think even Wigner will agree that
Okay.
yeah, they apply because, in a sense,
These
this is what they are.
people, they have a philosophical problem, okay. They are not philosophers, but they like philosophical problems.
Yeah.
But we are philosophers, we like also pragmatic problem. At the end, through mathematics and science, we are able to, not always, think the fields not of nature, of human sciences, economics, but also the description of complex systems, where you use mathematics just to describe, not to predict.
Yeah.
But anyway, prediction is the main target of the use of mathematics to study nature.
Yeah, okay. Yeah, there you go, Stefano, yeah.
Yeah, I mean, one way to explode the surprise is that, and this may be a kind of generalization of, I think the point a while ago was just ask, I mean, what would the world be like if math did not apply in any substantial way? And so you look back at basic programmatic statements by Descartes and everybody else, that math is the science of order, relational structures, and so forth. And so if that sort of thing did not apply to the universe, what kind of universe would we be living in? So the very fact that we do live in a universe where we've been able to get a handle on, I suspect I'm not really that interested in what's his name? Who was it? Planning it, yeah, planning it.
Yeah.
But I suspect that's sort of behind his question. Why is it we live in such an ordered world in the first place? And
Yeah,
I
yeah.
think it reduces the issue to that quite different sort of question.
I mean, if I can, just a quick, he's more into this sort of Keplerianism, Kepler's idea that God made the universe, the physical universe following mathematical laws. Therefore, there's no surprise that we're going to, as a human beings made in an image of God, we're going to discover the same. So it's, you don't have a puzzle, really, if you believe that. So, yeah, so it's all coming together.
And if you take any one particular thing, I mean, how much math, most of math does not apply to any particular question that we ask. We ask lots of questions about all kinds of things. So.
For questions.
Okay.
You want
I
to
really asked a question. Well, the one thing I want to say is that, when you say, oh, mathematics is made up of numbers and sets, that makes this question much more difficult to address. I mean, for example, if you think of ordinary basic systems in the physical world, you have things like atoms and molecules. What characterizes them? Simple geometric shapes. Plato was right about that. Characterized by simple symmetries. Solar systems characterized by simple symmetries. I mean, the key there is really geometry and geometric shape as an exhibition of symmetry.
Well, I think that the key here is how simple they are. I mean, SU2, for instance, or SU3, for instance, unitary symmetries, they're not really simple. So they come relatively late in the history of math. So.
Maybe they're not simple.
But the historical part should never be forgotten. So they are difficult for a caveman.
Absolutely, yeah.
They are very difficult at dinner time because, of course, everybody else was already there, ready to be used to produce that.
Right, representation theory, it's not just geometry. On the other hand, the lineage is from geometry, it's not from set theory and everything.
Oh no, yeah. And by the way, I don't think that maths is just numbers and sets. I think maths is not a reduction in various. So I mean, although if you insist, you can probably reduce everything. But real mathematics is more than just set theory. So yeah.
Actually, what can you do?
4 questions.
Yes, Fabio Sterpetti, Giovanna Corsi, Mirella Capozzi.
Okay, we can go on.
What
Yes.
can we do?
Maybe we can reduce the reading of Ruben Bay.
How long
If
possiamo
there are too many,
finish the bottle here.
Let's go on.
if there are too many,
Mr. Chairman, you are our ruler.
I
So
know,
rule us.
It's the boss.
can discriminate.
Cut the press.
Okay.
It's too late.
What is the
Yes.
question?
There is no-
Maybe, I don't know, maybe it's better to leave it to Mario. If not,
Yes, it's black.
okay, like Mirella, Fabio.
We can have
It was
more
just
5 more
one.
minutes.
I want to, I can talk
5
about
more
this
minutes.
after. if
Okay,
there is no
yeah.
time.
Yes. What about you?
Okay, just a very quick one. So about the simplicity. So mathematics, the aesthetic qualities of mathematics have this simplicity dimension. It's quite difficult to pin down, but it has something to do with simplicity. Now there are some very prominent views of laws of nature that also say that laws of nature are technically laws of nature by virtue of being simple, like the Pavia views. Laws of nature are the simplest regularities we find, and they are laws purely by virtue of that, more or less. Simple and powerful.
Yeah.
So given that sort of match, simplicity on this side and simplicity on that side, there may be a room for yet another
Good reason for
Reason.
the marriage to be fruitful.
Yeah. Yeah, I think that would work fine. It's just that we have to be a bit more, give more details in terms of what would a simple law look like, because you can always turn complicated laws and complicated formulations into simple ones just by introducing, new notation and stuff like that.
It
So
relates to the you had a quote from somebody who said that there's no reason to think why electrons wouldn't obey bodily laws.
yeah.
There are use of laws which make that almost impossible. We wouldn't consider them laws.
To observe an
Yeah.
isolated electron obeying Dirac equation, you should take special care.
Yeah.
There's nothing like that existing in the real world unless you separate the electron from all other electrons and you measure a single electron, and then it obeys Dirac equation. So you prepare, you look, and you find simple. But the world outside is a mess.
More instrumental.
Yeah.
Yeah, we can
Less
look at
philosophical, less
Nonetheless, we are able to make many things out of that. And
Yeah.
fly to the moon.
I'm going to stop here because we're too late. So thank you.